Today, let's discuss how medical data is normalized. The word normalize can have many meanings depending on where it's used. The dictionary defines it as to bring something to its usual condition, which could mean returning this to this. In other situations, normalize can mean changing data from one test result into different units of measurement. For example, converting ounces into milliliters or US pints, or converting a size measurement from inches to millimeters, feet, or yards. So as you can see, normalize can have a host of meanings, including calming tensions between nations at war. But in healthcare, to normalize data means converting common medical test results into units that convey levels of health or illness. It basically answers the question, are we healthy or sick? And if we're ill, how severe is the illness? To provide this information, we employ a statistical measurement known as a z-score. As an example, let's consider any blood test that has a range of values defining normal. Now, statisticians can demonstrate that those normal values would generate a bell-shaped curve. That tells us that most people have values that fall in the middle of the bell, while the remaining people spread out laterally in fewer and fewer numbers. The average for all healthy people under the curve is depicted at the peak and is represented by the Greek letter mu on the x-axis. Now, since different tests have different ranges for normal, we describe all numbers along the x-axis as being plus or minus the average. The next vertical demarcation line on the bell curve, shown here to the left and to the right of the average value, marks off what statisticians call one standard deviation. Now, a standard deviation is a statistical computation that defines the variation of test values within a group, which simply means the larger the standard deviation, the greater is the diversity of values within the group, and the more spread out would be the bell curve. However, the real importance of that value is that one standard deviation to the left and one standard deviation to the right of the average identifies test values found in 68% of the total population. At a distance of 2 standard deviations from the mean, that identifies an additional 27% of subjects, 13.5% on each side of the average value. Altogether, moving out 2 standard deviations either side of the average now includes 95% of the total healthy population. By convention, most medical clinicians use 2 standard deviations to identify health. Although 5% of the population can have test values falling under the left and right tail regions of the bell curve, those values would signify the upper or the lower normal values and would possibly be considered borderline signs of illness. Values that fall completely outside the range covered by the bell curve generally signify illness, and the farther away those values reside from the average value, the more severe is the degree of illness. Let's look at a specific example. Assume we are viewing the range of values associated with normal blood sugar. A given lab might report those values as between 80 and 100 milligrams per deciliter. As you can see, the average value for healthy subjects is 90 and therefore is depicted in the center of the bell. Since we know that 4 standard deviations contain 95% of the normal population, the values of 80 and 100 occupy those endpoints. Since we've already mentioned that different medical tests have different ranges for normal, it's much easier to remember what a test result conveys in terms of health if we use z-scores instead of the actual test result number. Depicting z-scores for our chosen population in this example, we see that a z-score of 0 would identify the average mean value, which means that a person with this score falls right in the middle of a healthy population. Range values for 1, 2, and 3 standard deviations below the mean are designated by a negative z-score, while standard deviations greater than the mean are designated with positive z-score values. Using this convention, one intuitively understands where any specific test result lies on a range of normalcy, and it doesn't require remembering the specific test result value. It also overcomes the handicap that different labs have different ranges of normal for the very same test. Lastly, another advantage of z-scores is that any test result can be normalized into a z-score using this formula. As an example, let's assume a person has a blood sugar that shows a value of 97 milligrams per deciliter. That result is inserted in place of the x within the formula, and now we also know from our example that the mean and standard deviation are 90 and 5 respectively. Therefore, substituting those values in the formula, we can calculate a z-score of plus 1.4. Recalling the bell curve, we know that that value falls to the right of the mean and under the upper limit of 2 standard deviations for normal. Hopefully this video gave you a better understanding of z-scores and how to calculate them for any test result with a normal range of values. If you like this information, please check our like box and subscribe to Informatics channel. Thank you.